When the United States and Israel launched Operation Epic Fury on February 28, 2026, the opening hours of the air campaign against Iran were unlike anything the world had seen in a generation. Over 1,700 targets were struck in the first 72 hours alone. Bunker-penetrating munitions fell on hardened underground nuclear facilities. Tomahawk cruise missiles severed command and control networks. B-2 Spirit stealth bombers flew round-trip missions from the continental United States to put 2,000-pound guided bombs through reinforced concrete. And threading through it all, penetrating the most heavily defended airspace in the Middle East without a trace on Iranian radar screens, was the aircraft that made all of it possible. The F-35 Lightning II was not simply a participant in Operation Epic Fury. It was the tip of the spear that made every other element of the campaign possible. The aircraft that went where nothing else could go and did what nothing else could do, night after night, for 39 consecutive days. Understanding the role the F-35 played in this campaign requires understanding what Iran had built to stop exactly this kind of attack. Over the preceding 2 decades, the Islamic Republic of Iran had invested an enormous proportion of its defense budget in a layered, integrated air defense network specifically designed to threaten American aircraft. The outer layer consisted of long-range surface-to-air missile systems, including Russian-supplied S-300 PMU-2 batteries, with engagement ranges exceeding 200 kilometers, capable of tracking and engaging aircraft at all altitudes from low-level ingress profiles up to the high-altitude cruise bands used by strategic bombers. Inside that layer, medium-range systems, including the indigenously developed Bavar 373, Iran's domestically produced answer to the S-300, provided overlapping coverage. Closer in, short-range systems including the Tor M1 and various other point defense weapons defended specific high-value sites like the Natanz enrichment facility and the Fordow underground complex. Radar coverage was layered with multiple frequencies to make it difficult for any single jamming solution to suppress the entire network simultaneously. This was not a paper air defense system. Iran had operated it, maintained it, and exercised it for years. The system was integrated with a command and control architecture designed to coordinate engagements across multiple batteries and radar systems simultaneously. When American planners drew up the strike packages for Operation Epic Fury, the Iranian integrated air defense network was the central planning problem. Every target set, every routing decision, every timing choice was shaped by the need to operate within, around, or through this system. The campaign solution began with the assets that could operate outside the integrated air defense network entirely. B-2 Spirit stealth bombers operating from Whiteman Air Force Base in Missouri flew missions exceeding 30 hours, carrying the massive ordnance penetrator, the 30,000-pound bunker-defeating weapon specifically developed to destroy the hardened underground facilities where Iran had buried its most sensitive nuclear activities. Fordow, cut deep into a mountain near Qom, was among the highest priority targets in the entire campaign, and required weapons that could only be delivered by the B-2. Tomahawk cruise missiles, launched from guided missile destroyers and submarines positioned in the Persian Gulf and the Arabian Sea, struck Iranian command and control nodes and air defense command facilities in the opening minutes, attempting to disrupt the integrated coordination that made the air defense network dangerous. But the B-2 fleet is tiny. The United States operates only 20 B-2 Spirits, a fleet so small and precious that every mission flown by every one of those aircraft represents a significant operational and strategic commitment. Tomahawks, however capable, are one-way weapons that cannot collect intelligence, cannot adapt to targets of opportunity, and cannot repeat their missions. Once the opening salvos were delivered and the B-2 bombers turned their noses back toward Missouri, the sustained penetration of Iranian airspace, the kind of persistent, high-tempo campaign that could systematically dismantle an entire military infrastructure target by target over 39 days, required an aircraft that could do what the B-2 did, but at operational scale. An aircraft that could fly the day after the opening strike, and the day after that, and the day after that, accumulating thousands of sorties into the most defended airspace in the Middle East without catastrophic losses. The United States amassed approximately 30 Air Force F-35 Lightning II fighters in the Middle East in the days leading up to the operation, drawing units from the 48th Fighter Wing at Royal Air Force Lakenheath in the United Kingdom and the 158th Fighter Wing of the Vermont Air National Guard. These were F-35 Alpha variants, the conventional takeoff and landing version operated by the Air Force. The 48th Fighter Wing at Lakenheath is one of the Air Force's most experienced F-35 units, having transitioned to the platform from the F-15C and D. Their positioning in the United Kingdom, just a few hours of flight time from the Middle East with tanker support, made them an immediately available asset when the decision to launch Epic Fury was made. The Vermont Air National Guard's 158th Fighter Wing had completed its own transition to F-35 Alphas and represented the kind of surge capacity that American air power planning counts on from the Guard and Reserve components in major contingency operations. On the opening night, as the first strikes went in, CENTCOM released imagery showing F-35 Charlie variants from the United States Marine Corps operating from the flight deck of the Nimitz-class carrier USS Abraham Lincoln, positioned in waters south of Iran. These were aircraft from Marine Fighter Attack Squadron 314, VMFA 314, the Black Knights, operating as part of Carrier Air Wing 9. The F-35 Charlie's larger wing, reinforced landing gear, and strengthened catapult attachment point make it the most range-capable of the three F-35 variants, with a combat radius estimated at over 1,200 kilometers. From the Abraham Lincoln's position in the northern Arabian Sea, the F-35 Charlie could reach targets throughout southern and central Iran without requiring tanker support within Iranian airspace, reducing the number of supporting aircraft that needed to operate in the threat environment. The USS Gerald R. Ford, the lead ship of the Navy's newest carrier class and one of the most powerful warships ever built, also contributed to the campaign from the Persian Gulf. The Ford's air wing included its own complement of strike aircraft and electronic warfare assets, with the EA-18G Growler playing a crucial role in suppressing Iranian radar systems in the outer threat rings that F-35ers then penetrated from the inside. The positioning of two carriers, one in the Arabian Sea providing access to Iran's southern coast and one in the Persian Gulf providing access to Iran's western approaches, created a geometric problem for Iranian air defense planners. The F-35ers were coming from multiple directions simultaneously, and there was no single orientation of Iran's air defense network that could optimally address threats from both axes at once. Later in the campaign, additional F-35B short takeoff and vertical landing aircraft arrived in theater aboard the USS Tripoli, an America-class amphibious assault ship that had transited from the western Pacific through the Malacca Strait and paused at Diego Garcia before proceeding to the Arabian Sea. The F-35B's unique lift system, which uses a shaft-driven lift fan in the forward fuselage and a three-bearing swivel nozzle at the tail to achieve vertical landing capability, allows it to operate from amphibious assault ships that lack the catapult and arresting gear systems of nuclear carriers. The Tripoli's arrival expanded the pool of available F-35 sorties and provided additional flexibility in how the aircraft could be positioned relative to Iranian targets. From the very first night of Operation Epic Fury, F-35ers were penetrating Iranian airspace. The opening strikes targeted the Iranian air defense network itself, with F-35ers mapping radar emissions and helping build the targeting picture that allowed subsequent strikes to systematically take down the air defense infrastructure layer by layer. Iran had invested decades and billions of dollars into this network, and it was not going to be destroyed in a single night. But the F-35's ability to operate inside that network, to fly through it collecting data while the outer layers were being suppressed by Growlers and struck by Tomahawks, gave American planners a real-time picture of what the air defense network looked like from the inside that no other platform could provide. The F-35's role in the campaign was far broader than strike delivery. In a conflict of this scale and complexity, the aircraft served simultaneously as the joint force's most capable intelligence, surveillance, and reconnaissance platform inside Iranian airspace, its primary electronic order of battle collector, and its forward sensor node for the networked kill chain. Every sortie an F-35 flew over Iran was generating data. The aircraft's sensors were identifying radar emitters by their frequency, waveform, and pulse repetition characteristics, building a constantly updated picture of where Iranian air defense systems were located, which ones were active, and which ones had been destroyed or gone silent. This targeting data was transmitted in real time through the aircraft's data links to the strike planning cycle, feeding directly into the selection and routing of subsequent strike missions. The ANAPG-81 radar in ground mapping mode was generating synthetic aperture radar imagery of Iranian facilities as the aircraft flew over them, providing battle damage assessment data that allowed planners to determine whether targets needed to be restruck. The electro-optical targeting system was imaging facilities in the infrared spectrum, showing heat signatures from facilities that were still operating and the cold signatures of ones that had been destroyed. This persistent intelligence collection from inside Iranian airspace, updating continuously throughout the campaign, was something no previous air campaign had possessed at this scale, and it made the systematic dismantling of Iranian military infrastructure across 39 days achievable in a way it would not have been with the intelligence collection assets available even a decade earlier. General Dan Kane, chairman of the Joint Chiefs of Staff, told reporters in mid-March that American forces were flying further to the east, penetrating deeper into Iranian airspace to hunt and kill one-way attack drone garrisons and destroy Iran's ability to project power outside its borders. This statement, delivered matter-of-factly at a Pentagon podium, should be understood for what it meant operationally. The eastern portions of Iran are further from the carriers and from the regional air bases where American aircraft were staging. They are closer to the core of the Iranian state, to the more densely populated and more heavily defended areas around Tehran and Esfahan and the Central Plateau. They are also where Iran's most significant drone manufacturing and storage infrastructure was concentrated. The facilities that were producing the Shahed series munitions that Iranian proxy forces were using against American allies and assets throughout the region. Flying further east into Iran meant flying longer distances into progressively more challenged airspace, without the benefit of being able to rely on the same density of electronic warfare suppression that covered the approaches from the south and west. The aircraft that could do this, that could penetrate deep into central Iran and find and destroy drone manufacturing facilities and Shahed storage garrisons and return to base, was the F-35. Not the F-15E, which is an extraordinary aircraft, but whose radar cross-section lights up Iranian air defense systems at ranges measured in tens of kilometers. Not the F-16C, which is one of the finest fighters ever built but which would require such extensive suppression support in eastern Iranian airspace that mounting effective strike packages would be logistically prohibitive. The F-35. The operational tempo that the campaign sustained over 39 days is itself a remarkable logistical and maintenance achievement. American forces flew over 13,000 sorties in total. Sustaining that tempo required not just the aircraft themselves, but a massive supporting infrastructure of tankers, maintenance personnel, spare parts, munitions, and intelligence processing capacity. The F-35's Autonomic Logistics Information System and its successor, the Operational Data Integrated Network, continuously monitor the health and status of every major system on the aircraft and generate predicted maintenance requirements before failures occur. In a high-tempo combat environment where aircraft are turning around for the next mission within hours of returning from the last one, this predictive maintenance capability is the difference between maintaining high availability rates and experiencing the kind of maintenance cascade that grounds an aircraft fleet at the worst possible time. The most consequential and operationally significant event involving an F-35 during Operation Epic Fury occurred on March 19th. A United States Air Force F-35 Alpha was flying a combat mission over Iran when it was struck by ground fire, believed by analysts to have been a surface-to-air missile engagement rather than small arms or other projectile, given the altitude at which F-35ers typically operate their combat profiles. The pilot sustained shrapnel wounds but retained aircraft control and successfully executed an emergency landing at an airbase in the region. CENTCOM confirmed that the aircraft landed safely, that the pilot was in stable condition, and that the incident was under investigation. The aircraft was described as damaged rather than destroyed, indicating that it remained repairable and would eventually return to flight status. To appreciate the full significance of what happened on March 19th, you have to place it in the context of the preceding 3 weeks of the campaign. The United States had flown over 8,000 combat sorties by that point. F-35ers had flown a substantial proportion of those missions directly over Iranian territory, including over the most sophisticated air defense installations the country possessed. The S-300 batteries, the Bavar 373 systems, the medium-range and short-range weapons defending specific high-value sites had all been given every opportunity to engage and destroy American aircraft. In over 3 weeks of continuous high-tempo combat operations against a determined adversary with capable air defense systems, the March 19th incident was the first confirmed combat hit on a fifth-generation stealth fighter in the history of aerial warfare. The Iranian government, specifically the Islamic Revolutionary Guard Corps, claimed credit for the engagement and released what it described as footage of the hit. The authenticity of the footage could not be independently confirmed, and American officials were notably cautious about providing any details that would help Iran understand what it had done differently on March 19 compared to the thousands of previous F-35 sorties it had failed to engage. What American officials confirmed was the essential fact: the aircraft was hit, the pilot was wounded, the aircraft landed under the pilot's own control, and the pilot survived. That sequence of events is the story of the F-35's design philosophy, made manifest in a single combat engagement. The aircraft got hit. That is notable but not surprising. In 39 days of continuous combat operations over a defended country, any aircraft will eventually absorb fire. The F-22, which is the only aircraft in the American inventory with arguably superior stealth performance to the F-35, has never been in comparable combat. The FB-2 had been hit by surface-to-air missiles during the 1999 Kosovo campaign, though that aircraft was lost after the crew ejected. What the F-35 demonstrated on March 19 was that when it gets hit, it does not go down. The pilot flew the damaged aircraft through Iranian airspace, across the intervening distance to a friendly airbase, and put it on the runway. The aircraft was recovered, and the program that had cost hundreds of billions of dollars to produce a fighter that could penetrate the most defended airspace on Earth and survive had delivered on its most fundamental promise. Iran subsequently claimed it had shot down a second F-35, this claim citing Mehr news agency reporting and carried by Reuters. CENTCOM did not confirm this claim, and, as of the campaign's conclusion, the official American tally of F-35 losses during Operation Epic Fury was 1 aircraft damaged and recovered, with no confirmed F-35 shootdowns. The broader American aircraft loss picture during the campaign was dominated by unmanned systems. Up to 24 MQ-9 Reaper drones were destroyed, accounting for over 60% of total aircraft attrition. 4 F-15E Strike Eagles were lost, 3 of them in the friendly fire incident involving Kuwaiti air defenses in the campaign's opening days, and 1 in a shootdown over Iran in April. 1 A-10 was shot down. The F-35, flying thousands of sorties into the most defended airspace in the Middle East, was hit once and flew home. By the time Operation Epic Fury concluded after 39 days, American forces had struck more than 10,000 targets throughout Iran, including underground nuclear facilities, ballistic missile production sites, naval vessels involved in mine-laying operations in the Strait of Hormuz, drone manufacturing infrastructure, and Iranian Revolutionary Guard Corps installations. Iran's ability to project power outside its borders through proxy forces was substantially degraded. Its nuclear program had been set back by years. Its air defense network, the investment of 2 decades of prioritized defense spending, had been dismantled to the point that American helicopters were flying over Iranian coastline without being engaged. None of this would have been achievable without the F-35. The aircraft that penetrated the defended target sets, the aircraft that collected the intelligence that built the targeting picture, the aircraft that flew the missions every other platform could not fly, was the F-35 Lightning II. To understand why the F-35 can do what it does, you need to understand both the physics of how it defeats detection and the engineering philosophy of how it was designed to fight once inside a defended environment. The F-35 Lightning II is a single-engine, single-seat, multi-role 5th-generation stealth fighter produced by Lockheed Martin at its facility in Fort Worth, Texas. There are 3 distinct variants sharing a common airframe and sensor architecture, but adapted to the different basing and operational requirements of the 3 American military services and allied customers. The F-35 Alpha is the conventional takeoff and landing variant. It takes off and lands like any other fixed-wing aircraft, using a conventional tricycle undercarriage and a standard engine exhaust nozzle. It is the lightest and fastest of the 3 variants and carries an internal 25mm gun in the port side root of the wing. The Alpha is operated by the Air Force and by the allied nations that have purchased the F-35 for conventional land-based air forces. Most of the roughly 30 F-35ers that participated in Operation Epic Fury as Air Force assets were Alphas. The F-35 Bravo is the short takeoff and vertical landing variant, operated by the Marine Corps, the British Royal Air Force, and the British Royal Navy. The Bravo's ability to take off in a short roll and land vertically without a runway comes from a propulsion system unlike anything previously produced in a supersonic combat aircraft. A shaft-driven lift fan, located immediately behind the cockpit in a bay that opens through doors in the upper and lower fuselage, is driven by the main engine through a clutch and driveshaft. During vertical operations, the lift fan generates several thousand pounds of downward thrust to support the aircraft's nose, while a 3-bearing swivel module at the rear of the engine deflects the main exhaust from horizontal to vertical to support the tail. Roll and pitch control during the hover are provided by reaction control valves at the wingtips, nose, and tail that use engine bleed air. The integration of all these systems in a supersonic airframe is one of the most complex mechanical engineering achievements in aviation history, and was the primary technical challenge that drove schedule delays and cost growth in the early years of the development program. The F-35 Charlie is the carrier variant designed specifically for catapult launches from and arrested landings on United States Navy aircraft carriers. The Charlie has the largest wing of the 3 variants, with folding wingtips to fit the space constraints of carrier hangars and elevators. The larger wing area provides more lift at lower speeds, which is important for safe carrier approaches, and contains additional fuel volume that gives the Charlie a combat radius exceeding 1,200 kilometers. The landing gear is substantially heavier and more robust than the Alphas, designed to absorb the punishing loads of arrested carrier landings, where the aircraft goes from 150 knots to 0 in about 2 seconds. The Charlie does not carry an internal gun, because the space that the gun occupies in the Alpha's airframe was needed for landing gear strengthening and fuel. When the gun is needed, the Charlie can carry an external pod, though this compromises the aircraft's stealth signature. All 3 variants share the same fundamental avionics architecture, the same sensor suite, and essentially the same mission system software. The commonality was the central promise of the Joint Strike Fighter program from its earliest days, and it was achieved to a degree that the program's skeptics never believed was possible, given the dramatically different physical requirements of a vertical landing aircraft and a carrier aircraft. The shared mission systems mean that pilots transitioning between variants need relatively minimal retraining in the aircraft's core fighting capability. They need to learn the different handling qualities and operational procedures of each variant, but the displays, the sensor integration, the weapons employment, and the tactical decision-making process are all the same. The foundational capability that makes the F-35 what it is begins with stealth. Stealth is frequently misunderstood as meaning that an aircraft is invisible to radar. It does not mean that. What it means is that the aircraft's radar cross-section is reduced to a level where enemy radar systems cannot reliably detect, track, and engage it at tactically significant ranges. Radar cross-section is measured in square meters of equivalent reflective area, and the difference between a conventional fighter and a stealth fighter in this metric is not linear. It is exponential. A 4th-generation fighter like the F-16C, in a typical combat configuration, has a radar cross-section roughly equivalent to a small car, perhaps 1 to 2 square meters, because of the clutter created by external weapons pylons, the engine intake, the cockpit canopy, and the inherently reflective geometry of a conventional fighter airframe. The F-35's radar cross-section has been estimated in public sources to be equivalent to a small metal sphere roughly the size of a golf ball, a value typically cited as approximately 0.001 square meters, or even lower. That is a reduction of 3 to 4 orders of magnitude. The engineering choices that produce this result touch every aspect of the aircraft's design. The airframe geometry uses carefully calculated edge alignment, ensuring that every leading and trailing edge of every surface reflects radar energy in the same directions. Rather than scattering radar returns across a wide range of angles, which would give adversary radars multiple detection opportunities at many aspects, the aligned edges concentrate the reflections into a small number of specific angles. Adversary radar systems only receive strong returns from the F-35 when they are positioned at very specific geometric relationships to the aircraft, and in practical tactical geometry, these windows represent a tiny fraction of the total aspect angles the aircraft presents during a typical mission. Radar-absorbing materials are applied to the aircraft's surface to convert radar energy that does reach the airframe surface into heat, rather than reflecting it back toward the emitting radar. These materials are carefully formulated to absorb energy across the frequency bands used by the threat radar systems the F-35 was designed to defeat. They are also one of the more maintenance-intensive aspects of the aircraft, requiring inspection and repair to maintain their performance to the specifications required for the low observable characteristics to be effective. The coating on a stealth aircraft is not a permanent treatment that can be ignored. It is a maintained surface that degrades through the normal wear of flight operations and must be periodically assessed and restored. The engine intake is a particularly challenging stealth problem because the highly reflective spinning compressor blades at the front of the engine, if directly visible to an opposing radar, would generate large and readily trackable radar returns. The F-35's intake uses a serpentine internal duct that bends the air path enough that the compressor face is never in a direct line of sight from the intake opening. Radar energy entering the intake travels down the duct, reflects off the curved walls, and arrives at the compressor face so attenuated that the compressor's reflective contribution to the aircraft's total radar cross-section is negligible. The trade-off is that the curved duct introduces some aerodynamic inefficiency compared to a straight intake, but the stealth benefit was judged to far outweigh the small performance penalty. The most operationally significant aspect of the F-35's stealth architecture is its internal weapons carriage. External stores represent an enormous proportion of a fighter aircraft's radar cross-section. The pylons, bombs, missiles, and targeting pods hanging below the wings of a fourth-generation fighter in a typical combat configuration dramatically increase the aircraft's detectability in ways that cannot be mitigated by any amount of radar-absorbing coating on the airframe itself. The F-35 carries all weapons in two internal bays running along the ventral surface of the aircraft. The bay doors open briefly to allow weapons release, then close again, restoring the clean, low-observable geometry. In this configuration, the aircraft's stealth performance is maintained from takeoff through weapons release and return to base. The internal bays can carry a variety of weapons in different configurations depending on the mission. In a standard air-to-air configuration, each bay holds one AIM-120 AMRAAM beyond visual range missile, for a total of 2. In a standard air-to-ground configuration, each bay holds one 2,000-pound Joint Direct Attack munition and one AIM-120, giving the aircraft both air-to-air and air-to-ground capability simultaneously. For missions requiring more ground attack capacity, the bays can carry 2 GBU 32 1,000-pound JDAMs each for a total of 4, or 4 GBU 39 250-pound small-diameter bombs, each for a total of 8 separate aim points. This flexibility allows the crew to configure the aircraft's strike capacity to the specific requirements of each mission while always maintaining a self-defense air-to-air capability. When the stealth requirement is relaxed, in environments where the threat no longer justifies the restrictions imposed by internal carriage alone, the F-35 can carry additional weapons on 6 external hardpoints, 3 under each wing. In this beast mode configuration, the aircraft can carry an additional weapons load approaching 16,000 additional pounds, dramatically expanding its strike capacity at the cost of the low observable performance that makes it survivable in contested airspace. In Operation Epic Fury, Beast Mode would have been available for strike missions against targets in the Iranian interior once the air defense network in a given area had been sufficiently degraded that the full stealth configuration was no longer required to survive the ingress and egress. The sensor suite that the F-35 uses to find, classify, and engage targets is built around the concept of sensor fusion, a term that describes something far more significant than simply having multiple sensors on the same aircraft. The AN/APG-81 Active Electronically Scanned Array Radar is the primary active sensor. The AESA architecture uses an array of roughly 1,500 individual transmit-receive modules, each a tiny solid-state radar element that can be independently controlled in terms of frequency, phase, and amplitude. By precisely controlling the phase relationships between these elements, the beam of the radar can be electronically steered to any point within the radar's field of regard in microseconds, without any mechanical antenna movement. This beam agility allows the radar to perform multiple functions simultaneously in ways that are impossible for a mechanically scanned radar. In air-to-air mode, the APG-81 can maintain continuous tracks on multiple airborne contacts simultaneously while searching for new ones, a fundamental advantage over mechanically scanned radars that must choose between searching and tracking. In air-to-ground mode, the radar generates synthetic aperture radar imagery of ground areas with resolution sufficient to identify individual vehicles and building structures, and performs ground-moving target indication to detect and track vehicles moving below the aircraft. In electronic attack mode, the radar can direct focused beams of radio frequency energy at specific threat emitters, jamming their ability to operate effectively. In low probability of intercept mode, the radar spreads its emissions across a wide range of frequencies and varies its waveforms continuously to make its own emissions difficult for adversary electronic intelligence systems to detect and characterize. A radar warning receiver on an adversary aircraft or ground system that receives emissions from the APG-81 may not recognize them as radar emissions at all. The APG-81's ability to operate in low probability of intercept mode is particularly important for stealth operations. A fighter using a conventional radar in combat is broadcasting its presence to every radar warning receiver within range. The APG-81 allows the F-35 to actively use its radar, while maintaining the aircraft's overall low observable profile in the electromagnetic spectrum. This does not make the radar invisible to a sophisticated electronic intelligence system with sufficient collection capability, but it substantially reduces the range at which the radar's emissions can be detected and characterized, contributing to the overall picture of an aircraft that is very difficult for adversary systems to find and track by any means. The electro-optical targeting system is embedded into the lower forward fuselage beneath a multifaceted sapphire glass aperture that is itself shaped to contribute to the aircraft's stealth geometry. The EOTS is the successor to the targeting pods carried externally on fourth-generation fighters, but its integration into the airframe means it is always available without compromising stealth and without consuming a weapon's hardpoint. The system provides a high-resolution forward-looking infrared sensor that generates thermal imagery at multiple fields of view, from wide-area search down to narrow-field identification, a mid-wave infrared sensor for detecting the thermal signatures of aircraft engines and missile plumes, a high-definition color television camera for daylight visual identification, a laser rangefinder for computing precise slant range to designated targets, and a laser designator that can illuminate targets for laser-guided bomb guidance. The EOTS is stabilized against aircraft motion with sufficient precision to maintain a steady image in a stable laser spot during high-G maneuvering, which is essential for accurate weapons delivery. The distributed aperture system is the capability that most dramatically distinguishes the F-35's pilot situation awareness from that of any previous fighter aircraft. 6 infrared camera assemblies are distributed around the aircraft's fuselage at positions that provide complete spherical coverage with no blind spots anywhere around the aircraft. The imagery from all 6 cameras is processed and fused by the mission computer into a seamless spherical picture. This fused imagery is projected onto the visor of the pilot's helmet-mounted display, mapped to match the pilot's actual visual perspective regardless of which direction the pilot is looking. The operational implications of this capability are profound and extend far beyond the obvious ability to see what is behind and below the aircraft. For missile approach warning, the DAS provides continuous automatic scanning of the entire sphere around the aircraft for the specific infrared signature of a rocket motor plume. A missile fired from any direction at any aspect is detected automatically by the DAS within the first seconds of its burn, and the crew is immediately cued with bearing, range, and weather countermeasures have been dispensed. This automatic passive all-aspect missile warning capability is something no previous fighter has possessed. Previous missile approach warning systems required the aircraft to be in certain attitudes, or had coverage gaps in specific aspects, or required the crew to be monitoring a display rather than providing automatic attention-getting cues. The DAS also provides the pilot with a persistent view of the environment below the aircraft in a way that allows nap of the Earth flight at night without requiring the pilot to stare at a separate navigation system display. Looking down through the floor gives the pilot the same infrared view of terrain that forward-looking infrared systems have always provided, but accessible simply by looking in that direction rather than being confined to a fixed forward field of view. In a terminal approach to a target, where the pilot may be maneuvering aggressively while the gunner in the targeting system engagement, the ability to simply look in any direction and see that direction in the infrared provides a fundamental safety and situational awareness benefit that cannot be replicated by any number of separate displays. The helmet-mounted display system Generation 3 is the interface through which the pilot receives all of this sensor information. The helmet costs approximately $400,000 per unit, which is itself a remarkable figure, though it represents an extraordinarily small fraction of the total aircraft cost. The helmet contains a high-resolution display projected across both eyes with a wide field of view, a head tracking system that determines the helmet's precise orientation in 3 dimensions to align the DAS imagery with the pilot's actual visual perspective, night vision sensors, and all the associated electronics to drive the display at the update rates required for a seamless visual experience. The helmet does not merely display DAS imagery. It presents the pilot with a fused picture that integrates the DAS's raw infrared imagery with computer-generated symbology showing the locations of tracked contacts, threat assessments, weapons envelopes, navigation information, and any other data the pilot needs to be aware of, all overlaid on the visual scene in a way that allows the pilot to understand both what the sensors are detecting and what the aircraft knows about those detections without looking away from the outside world. When a threat radar illuminates the aircraft, a symbol appears in the pilot's visual field showing the direction to the threat. When a contact is tracked and assessed as hostile, its symbol appears positioned in the sky where it actually is. When a weapons envelope is calculated, its boundaries are visible in the pilot's field of view as if drawn on the sky itself. This is not merely a heads-up display. It is a fundamentally different relationship between the pilot and the information the aircraft possesses. Sensor fusion, the process of correlating and integrating all of the data from all of the aircraft's sensors into a single coherent tactical picture, is the operational capability that makes all of this technology militarily decisive rather than merely impressive. A fighter that has excellent radar and excellent infrared sensors and an excellent electronic warfare receiver, but presents all 3 to the pilot as separate displays, generates information overload. The pilot must mentally integrate 3 separate pictures, each with its own symbology, each updating at its own rate, each representing the world from its own sensor perspective. In the time-compressed environment of combat, this mental integration is a limiting factor on how quickly the pilot can make decisions and how much information can be processed before something important is missed. The F-35's mission computer performs this integration automatically, continuously, and in real time. Every contact detected by any sensor is correlated against contacts detected by every other sensor. A contact that appears as a radar return in the APG-81 is also examined for an infrared signature in the EOTS and a radio frequency emission in the electronic warfare suite. If all 3 sensors detect consistent data from the same location, the mission computer combines them into a single merged track with a high confidence classification. If only one sensor detects something, the track is shown with appropriate uncertainty. If the electronic warfare suite identifies a radar emission as belonging to a specific threat system type, the mission computer draws on its threat library to assess the engagement capability of that system and displays the threat's estimated lethal engagement zone as a bubble in the pilot's picture. The pilot sees not just where threats are, but what they can do. This fused picture is shared with the other aircraft in the formation and with the broader joint force through the aircraft's data links. The multifunction Advanced Data Link, MADL, is a low probability of intercept directional communications link that allows F-35As to communicate with each other and with B-2 bombers without generating the detectable radio frequency emissions that conventional data links produce. In a formation of F-35As flying deep into Iranian airspace, each aircraft is sharing its sensor picture with every other aircraft, building a collective awareness of the battle space that is richer than what any single aircraft could develop alone. An F-35 detecting a threat from one aspect contributes that information to the entire formation's picture. An F-35 that has just designated a target with its laser and launched a weapon can share the targeting data with a wingman whose sensors are better positioned to provide battle damage assessment. The aircraft's Link 16 capability connects this stealth formation to the broader joint force, allowing the F-35 to serve as a gateway between the stealth network operating inside Iranian airspace and the conventional network of fourth-generation aircraft, ships, and ground stations operating in the outer layers. When an F-35 identifies an air defense system inside Iranian airspace that the outer layer assets cannot see, it can transmit that identification through Link 16 to the Joint Forces strike planning process in near real time, potentially triggering a Tomahawk strike or directing a Growler jamming beam before the crew's aircraft has even completed its egress from the threat area. The F-35's electronic warfare suite, the ANASQ-239 system, provides the aircraft with capabilities that in previous generations of aircraft would have required a dedicated electronic warfare platform. The suite includes electronic support measures that passively listen for and identify radar emissions across a wide frequency range, comparing them against an onboard threat library to classify threat systems. It includes electronic attack capability that can jam specific threat systems using the aircraft's own apertures, including the APG-81 radar operating in jamming mode against specific emitters. And it includes self-protection features that automatically manage the aircraft's expendable countermeasures, chaff and flares, in response to detected threats. The integration of the electronic warfare suite with the rest of the sensor and communications architecture means that when the suite detects an Iranian radar system operating at a specific frequency with specific waveform characteristics, that information is immediately merged with any radar and infrared data the other sensors have on the same geographic area, correlated with the threat library to produce a system identification, and presented to the pilot as a single merged data point in the fused tactical picture. Simultaneously, the information is transmitted to the rest of the formation through MADL and to the Joint Force through Link 16. The F-35 is not just an aircraft that can protect itself from electronic threats. It is an aircraft that contributes to the collective electronic warfare picture of the entire Joint Force by virtue of its ability to operate in positions where no other sensor can survive. The weapons the F-35 employs span the full range of the American precision strike inventory. For air-to-air combat, the primary weapon is the AIM-120D Advanced Medium-Range Air-to-Air Missile, the latest production variant of the AMRAAM family. The AIM-120D uses an active radar seeker for autonomous terminal homing after the aircraft has provided a launch solution, giving it fire-and-forget capability. Its range, classified at the specific performance level, but estimated in open sources to exceed 180 kilometers in optimal engagements, allows the F-35 to engage airborne threats well beyond visual range from a position of stealth that denies the adversary even the knowledge that the firing aircraft exists until after the missile has been launched. Shorter-range air-to-air engagements can employ the AIM-9X Sidewinder, a highly agile infrared-guided missile that can be employed at off-boresight angles well beyond the aircraft's heading, cueing off the helmet-mounted display's ability to slave the seeker to wherever the pilot is looking. For the close-in air-to-air engagement that becomes necessary if an adversary survives beyond visual range engagement, the F-35 Alpha's internal gun is the GAU-22/A, a 4-barrel 25mm rotary cannon derived from the GAU-12/U used in the AV-8B Harrier. The weapon fires at approximately 3,300 rounds per minute and carries 180 rounds in the standard internal load, enough for approximately 3 to 4 seconds of continuous fire. The 25mm caliber is somewhat smaller than the 20mm M68 tone gun used in earlier Air Force fighters, and some critics have argued that this represents a step backward in gun capability. The program's response is that the gun is a last resort weapon in an aircraft designed to win engagements at beyond visual range before the close-in fight ever begins, and that the gun's weight and volume requirements place real constraints on what could be accommodated internally in the aircraft's compact fuselage. For air-to-ground strike missions, the GBU-31 Joint Direct Attack Munition is the workhorse weapon. The JDAM uses GPS guidance to steer a standard Mark 84 2,000-pound bomb to within approximately 5 meters of its designated coordinates, regardless of weather, cloud cover, or visibility conditions. The GPS guidance makes it immune to the limitations of optically guided weapons that require the designating aircraft to maintain laser contact with the target through the bomb's time of fall. For smaller targets, or where limiting collateral damage is important, the GBU-32 1,000-pound JDAM and the GBU-38 500-pound JDAM provide the same GPS precision in smaller warhead packages. The GBU-39 small-diameter bomb takes this miniaturization further, with a 250-pound warhead and folding wings that allow glide delivery from high altitude to targets over 60 miles from the aircraft's position, allowing the F-35 to strike multiple targets on a single pass with minimal exposure to any one target's point defenses. The GBU-53/B Stormbreaker, previously designated the Small Diameter Bomb 2, represents the most capable precision strike weapon the F-35 carries for challenging target sets. Its tri-mode seeker combines millimeter-wave radar for all-weather autonomous target acquisition, imaging infrared for visual identification and precise aim point selection, and semi-active laser homing for engagement when a ground or airborne designator is providing laser illumination. The combination of these three modes allows the Stormbreaker to engage moving targets in any weather condition, a capability that previous precision-guided munitions lacked entirely. A tank column moving across the Iranian desert in a sandstorm presents a Stormbreaker with the same engagement opportunity it presents in clear weather, because the millimeter-wave radar seeker is immune to atmospheric effects that would defeat optical and infrared seekers. The weapon's glide range of over 60 miles from high-altitude delivery also allows the F-35 to engage even well-defended target areas without overflying them directly. Longer-range standoff weapons being integrated into the F-35's weapons suite extend its reach further still. The AGM-158 Joint Air-to-Surface Standoff Missile, JASM, is a stealthy cruise missile with a range approaching 350 miles in its baseline variant and over 500 miles in the extended-range AGM-158B. The JASM's own low observable design means that even after the F-35 releases the weapon from well outside Iranian air defense coverage, the missile's approach to the target is itself a stealth penetration problem for Iranian radars. The AGM-158C Long-Range Anti-Ship Missile, LRASM, adapts the JASM extended-range airframe for the anti-ship mission, providing the F-35 with a precision, autonomous, long-range capability against the naval targets that were a significant component of the Operation Epic Fury target set, including the Iranian fast attack vessels and mine-laying ships operating in the Strait of Hormuz. The F-35's performance characteristics reflect the trade-offs of a design that prioritizes sensors, stealth, and payload breadth over raw speed and maneuverability. The aircraft's maximum speed is approximately Mach 1.6, achieved in dry thrust without afterburner. This is slower than the F-22 at Mach 2.2 and slower than the F-15C at Mach 2.5, and critics of the program have pointed to this as evidence that the F-35 compromised too much in the performance dimension. The program's response, which has been validated by operational experience, is that an aircraft whose stealth characteristics allow it to engage adversary aircraft before those aircraft ever detect its presence does not win dogfights through superior speed or turn rate. It wins them by firing missiles from beyond visual range at adversaries who do not know they are being targeted. Speed and turn performance matter in within visual range combat. But within visual range combat is what happens when beyond visual range weapons have failed. An aircraft designed from the ground up to win before the fight gets to that range is making a rational trade-off. The F-35 does carry afterburner capability, with the Pratt & Whitney F-135 engine providing approximately 43,000 pounds of thrust in full afterburner. The single F-135 turbofan is one of the most powerful fighter engines ever produced, and its performance in the F-35's approximately 35,000-pound empty-weight airframe gives the aircraft a thrust-to-weight ratio approaching 1-to-1 in a typical combat configuration. The fly-by-wire flight control system optimizes aircraft response across the entire flight envelope and provides carefree handling characteristics that allow the pilot to focus on the tactical situation rather than managing the aircraft's angle of attack and speed limits manually. The history of how the F-35 came to exist is itself one of the most complex and consequential stories in the history of military aviation. To understand it properly requires going back not just to the Joint Strike Fighter competition of the 90s, but to the strategic and technological context that made such an ambitious program conceivable. In the mid-1980s, the United States Air Force was developing what would become the F-22 Raptor as its next-generation air superiority fighter. The F-22 program, then known as the Advanced Tactical Fighter, was pursuing genuinely revolutionary capabilities including supercruise, the ability to fly supersonically without afterburner, and what was then called super maneuverability, the ability to use thrust vectoring to control the aircraft at extremely high angles of attack where aerodynamic surfaces lose effectiveness. The F-22 was also designed around stealth from its first conception, making it the first operational fighter in history designed with low observable characteristics as a primary requirement rather than an afterthought. The F-22 was going to be expensive, very expensive, and the Air Force needed it in large quantities to replace its aging F-15C and D air superiority fleet The tension between the unit cost, driven by the aircraft's complexity, and the quantity needed to replace the fleet it was designed to succeed was apparent from early in the program. As the Cold War ended and defense budgets contracted through the 90s, this tension became acute. The Air Force had initially envisioned procuring over 700 F-22s. By the time the aircraft entered service, that number had been cut to 340, then to 187, the number eventually produced, in what became one of the most consequential procurement decisions in Air Force history. The cost of developing the F-22 and the recognition that the unit cost of such a sophisticated aircraft would limit the quantities that could be purchased drove the search for a lower-cost complement. The logic was clear. The Air Force needed both a high-end air superiority fighter that could defeat the best adversary fighters in beyond visual range in close combat, and a lower-cost multi-role fighter that could be purchased in the quantities needed to replace the numerically large F-16C fleet across the Air Force and the Air National Guard. These did not need to be the same aircraft. They needed to be complementary. With the F-22 handling the highest threat air superiority mission, and the lower-cost multi-role aircraft handling the strike and close air support missions that constituted the bulk of the Air Force's day-to-day operational demand. The Marine Corps had been operating the AV-8B Harrier since the early 1980s. The Harrier's short takeoff and vertical landing capability was central to the Marine Corps' expeditionary warfare concept, allowing fixed-wing aviation support to operate from ships and austere land bases that lacked conventional runways. The Harrier was an effective aircraft within its performance limits, but those limits were real. It was subsonic, its payload was modest. Its avionics were, by the late 80s, increasingly dated. The Marines needed a replacement that could provide the same basing flexibility with the performance of a modern combat aircraft, and they had been watching the DARPA ASTOVL program with considerable interest since its beginnings in the mid-80s. The DARPA ASTOVL program explored several lift system concepts for a supersonic short takeoff and vertical landing aircraft. The challenge is substantial. A conventional fighter uses its engine exhaust for propulsion, directing all thrust rearward to generate forward motion. A vertical landing aircraft needs to direct thrust downward to support the aircraft's weight in the hover. Doing both simultaneously, or switching rapidly between them, while maintaining supersonic performance in forward flight, requires a propulsion system architecture that conventional turbofan engines cannot provide without fundamental redesign. Several concepts were explored, including remote augmented lift systems that used engine bleed air directed to nozzles in the wings and nose, shaft-driven lift fans, and three-bearing swivel nozzle systems. Lockheed's concept combined a shaft-driven lift fan forward with a three-bearing swivel nozzle aft, an approach that distributed the vertical lift load between two sources and allowed the main engine to remain optimized for forward flight, while the lift fan provided the downward thrust. This architecture was more complex than alternatives, but offered better efficiency in the hover and better integration with a supersonic airframe design. The Navy had separate requirements driving from a different direction. The F-14D Tomcat was aging, and while the F/A-18E/F Super Hornet was being developed as its replacement, the Navy recognized that the Super Hornet, while a significant improvement over the earlier F/A-18C/D, was still a fourth-generation aircraft, with the signature and sensor limitations that implied. A stealthier, more capable complement to the Super Hornet for the most demanding penetrating strike missions would be needed as adversary air defense systems improved. The bottom-up review of 1993, conducted by the Defense Department under Secretary Les Aspin in response to the end of the Cold War and the need to restructure American military forces for the post-Soviet world, addressed these overlapping requirements. The review recognized that the Air Force's affordable multi-role fighter requirement, the Marine Corps' Harrier replacement requirement, and the Navy's penetrating strike requirement had enough in common that attempting to address them with separate programs would be prohibitively expensive. The Joint Advanced Strike Technology Program, JAST, was established to explore how common airframe and avionics technology could meet all three requirements. JAST operated as a technology program rather than a formal acquisition program for its first couple of years, conducting studies and trade analyses to determine what level of commonality was achievable across the three service requirements without unacceptably compromising any one service's needs. The analysis found that a high degree of commonality in the avionics, mission systems, and structural approach was achievable, and that the major physical differences between the variants, primarily the short takeoff and vertical landing propulsion system for the Marine Corps variant and the strengthened carrier structure for the Navy variant, could be accommodated through defined variants from a common baseline rather than through entirely separate designs. In 1994, the program was renamed the Joint Strike Fighter and structured as a competitive acquisition. Two industry teams were selected for the concept demonstration phase in 1996. The Boeing team, building on Boeing's experience with the X-32 design it had submitted in the earlier competition, proposed an aircraft with a distinctive cranked delta wing and a direct lift system using a modified main engine nozzle for vertical landing. The Lockheed Martin team, working with Northrop Grumman and British Aerospace as principal partners, proposed a design that would become the X-35, incorporating the shaft-driven lift fan concept from DARPA's ASTOVL work. Both teams built two prototype aircraft, and the fly-off evaluation began in the fall of 2000. The Boeing X-32B made its first short takeoff and vertical landing flights in March 2001, demonstrating the baseline capability required. But the Lockheed Martin, the 1035B, achieved something more dramatic. In what became known as the Mission X flight, the X-35B took off from a short field run, accelerated to supersonic speed in level flight, transitioned to vertical landing mode, and set the aircraft down vertically, all in a single, uninterrupted flight profile. No aircraft with supersonic capability had ever done this before. The Harrier achieved vertical landing but was subsonic. The X-35B was supersonic and vertically landed, and it did so in the same flight without any intermediate landing to reconfigure. In October 2001, the Defense Department selected Lockheed Martin as the winner of the Joint Strike Fighter competition. The announcement came just weeks after the September 11th attacks, in a defense environment that was already shifting toward the requirements of the conflicts that would define the next 2 decades. The program was formally designated the F-35 Lightning II, and the system development and demonstration phase began, targeted at delivering a production-ready aircraft for all 3 variants. The system development and demonstration phase ran from 2001 through approximately 2015 and was one of the most technically challenging defense development programs in American history. The simultaneous development of 3 variants sharing a common core, combined with the unprecedented complexity of the sensor fusion and mission systems software, generated cost growth and schedule delays that became a persistent subject of congressional scrutiny and multiple program restructurings. The software development challenge was the largest single source of schedule pressure. The F-35's mission systems software, when the full Block 4 capability is included, comprises tens of millions of lines of code. The sensor fusion algorithms must process data from 6 different sensor sources in real time, maintaining coherent tracks on dozens of contacts simultaneously while managing weapon system states, communications protocols, navigation data, and threat assessments. The electronic warfare suite management must monitor hundreds of frequency channels and make autonomous jamming and countermeasure decisions in microseconds. All of this code must work correctly every time in every operational scenario, because a software failure in combat can be fatal in ways that a software failure in a business application is not. The validation process for this software requires running every line of code through a comprehensive test suite that exercises every operational scenario the aircraft might encounter. This testing was done first on the Iron Bird, a ground-based avionics test facility that replicates the complete mission systems architecture of the flying aircraft, and then on instrumented flying aircraft in an environment that could generate every combination of sensor inputs, aircraft states, and weapons conditions that the software would encounter in operations. The sheer scale of this validation effort drove schedule delays that cascaded through the entire program, delaying each successive software build and pushing the dates for the various operational capability milestones further into the future. Cost growth was the other persistent challenge. The program's development cost estimate grew from the original 1990s projection of approximately $22 billion to over $55 billion by the time development was complete. Unit production costs grew substantially from the figures cited in early program justifications, peaking at over $100 million for the F-35 Alpha in early production lots, when the production rate was low and learning curve effects had not yet driven down manufacturing costs. The Nunn-McCurdy thresholds, which require congressional notification and program review when a major defense acquisition program's unit cost exceeds the baseline estimate by specified percentages, were breached multiple times, triggering the formal review and restructuring processes that led to program schedule extensions and reductions in near-term production quantities. The criticism the program received during this period was sometimes well-founded, and sometimes reflected a misunderstanding of what was actually being built. The valid criticisms included the genuinely optimistic early cost estimates that reflected political pressure to make the program appear affordable rather than realistic engineering analysis. The program management during its early years did not always have the rigor required to identify cost and schedule problems early enough to manage them effectively. The concurrent development and production strategy, which began producing aircraft before development was complete and before the design was fully stable, resulted in expensive retrofits to early production aircraft when development testing revealed deficiencies. The criticisms that reflected misunderstanding included the argument that the performance trade-offs made to achieve commonality across three variants had produced an aircraft that was inferior to the fourth-generation fighters it was replacing in every individual performance metric. This argument is technically partially true, in that the F-35 is slower than an F-15C and less agile at high angles of attack than an F-16C in a within-visual range turning engagement. But it fundamentally misunderstands the design intent. The F-35 was not designed to be a better F-15C or a better F-16C in the same kinds of fights those aircraft were designed for. It was designed to fight in an entirely different way, to operate in environments where the F-15C cannot survive, to engage adversaries before they know the F-35 exists, and to function as a networked joint force node rather than a standalone fighting platform. Comparing the F-35 to the F-16C on a turn rate chart is like comparing a submarine to a destroyer on top speed. The metrics that matter for the mission are not the same. The program's defenders also pointed to the aircraft's unprecedented breadth of capability as justification for its cost. No previous fighter in history has simultaneously provided the air-to-air capability of a dedicated air superiority fighter, the precision strike capability of a dedicated strike aircraft, the electronic warfare capability of a dedicated jamming aircraft, the intelligence collection capability of a dedicated reconnaissance aircraft, and the command and control integration capability of a networked operations center, all in a single platform that a single pilot can fly. The F-35 is not just a fighter. It is the hub of an air operations network, and its individual unit cost, while genuinely high, must be evaluated against what it replaces and what it enables across the broader joint force. The Marine Corps declared initial operational capability with the F-35B in July 2015, becoming the first service to field the aircraft. The Marines had the most urgent operational need, as the AV-8B Harrier fleet was aging and its replacement could not be delayed further without accepting a gap in the service's short takeoff and vertical landing strike capability. The F-35B's initial operational capability represented the culmination of over a decade of development and the validation of the lift system architecture that had been the program's most technically demanding element. The Air Force declared initial operational capability with the F-35A in August 2016, followed by the Navy with the F-35C in February 2019. Each service's IOC declaration was accompanied by a rigorous evaluation of whether the aircraft could perform its primary missions with sufficient reliability to be deployed to combat. The Navy's IOC declaration was the last because the carrier variant required the most extensive testing of the catapult and arrested landing systems, and because the modifications required to fully certify the F-35C's structural integrity for carrier operations took longer than anticipated. The F-35's first confirmed combat use came from an unexpected direction. On May 22, 2018, Israeli Air Force Chief General Amikam Norkin announced at a conference that Israeli F-35 Adir aircraft had conducted strikes inside Syria, describing the aircraft as the first F-35 to attack targets in the Middle East. The Israeli Air Force had received its first F-35 Adirs in December 2016 and had moved aggressively to integrate the aircraft into combat operations as quickly as the program's incremental capability releases would allow. Israel had significant motivation to do so. Syria in 2018 was protected not only by Syrian national air defense systems, but by Russian-operated S-400 surface-to-air missile systems deployed at the Chimimim Air Base, systems with the capability to track and engage Israeli aircraft over Syrian territory. The Adir is not simply an off-the-shelf F-35A. Israel negotiated specific modifications as part of its purchase agreement, including integration of Israeli-developed electronic warfare systems, the ability to carry Israeli-developed weapons in the internal bays, and modifications to certain software and hardware elements to accommodate Israeli operational requirements and classified national security considerations. The Adir designation reflects these Israeli-specific modifications and the aircraft's significance to the Israeli Air Force's capability portfolio. Israel is one of only two countries, the other being the United Kingdom, that has negotiated modification rights that allow it to integrate its own systems into the F-35, rather than being limited to the standard configuration. Following the initial Syria strikes, Israeli F-35 Adirs accumulated a steady operational record over the subsequent years, participating in the multi-year campaign of strikes in Syria targeting Iranian weapons transfers to Hezbollah, drone and missile manufacturing facilities, and Iranian military infrastructure. These operations, collectively known in Israeli military parlance as the Campaign Between the Wars, validated the F-35's operational concept in a real combat environment involving sophisticated threat systems on a sustained basis. The data from these operations, including information on electronic emissions that the aircraft's sensors collected during each sortie, contributed to intelligence about Iranian and Russian air defense systems that directly informed American planning for Operation Epic Fury. The United States Marine Corps achieved its own F-35 combat first in September 2018 when aircraft from Marine Attack Squadron 211, the Avengers, operating from the USS Essex amphibious assault ship during a deployment to the Persian Gulf, dropped GBU-12 Paveway, 2 laser-guided bombs on Taliban targets in Afghanistan. The mission validated the F-35's close air support capability in an actual combat environment and marked the first time any United States F-35 had released weapons in combat. The Essex deployment demonstrated the F-35B's ability to operate effectively from an amphibious assault ship in a combat zone, validating the operational concept that the Marine Corps had built around the aircraft's basing flexibility. British Royal Air Force F-35Bs conducted their first combat strikes in June 2019, dropping Paveway the 1V laser-guided bombs on ISIS targets in Syria and Iraq from the Royal Air Force Base at Akrotiri in Cyprus. This marked the United Kingdom's entry into the growing list of nations that had employed the F-35 in combat and validated the RAF's transition to the platform after years of operating the Tornado GR-4 in the strike role. The British F-35Bs subsequently deployed aboard HMS Queen Elizabeth for the carrier's first operational deployment in 2021, operating alongside United States Marine Corps F-35Bs in a combined Anglo-American carrier air wing that represented a new model of Allied carrier aviation integration enabled by the common platform. By the time Operation Epic Fury began, the collective F-35 combat record across the United States services, Israel, and the United Kingdom had validated the platform's fundamental capabilities in a range of real-world operational environments, from the relatively permissive airspace of Afghanistan to the more challenging electronic environment of Syria with its Russian and Syrian national air defense systems. This validation was important not just as program justification, but as evidence that the aircraft's design premises were correct, and that the operational concepts built around it were sound. The crews who flew the F-35 into Iranian airspace on February 28, 2026, were flying an aircraft whose capabilities had been demonstrated in combat, refined through operational experience, and continuously improved through the software upgrade process that the program's open architecture enabled. The Block 4 Capability Upgrade Program, ongoing at the time of Operation Epic Fury, represents the most comprehensive improvement to the F-35's capabilities since the aircraft entered service. The upgrade is delivered through 2 simultaneous tracks: the Technology Refresh 3 hardware upgrade, which replaces the mission computer hardware with a new architecture based on commercial derivative processing chips that provide approximately 25 times the processing speed and substantially more memory than the original integrated core processor, and the Program Increment 14 software build, which uses the additional processing capacity to implement more advanced sensor fusion algorithms, improved electronic warfare management, enhanced targeting capabilities, and the Technology Refresh 3 hardware upgrade is significant, not just for its immediate performance benefits, but for the upgrade capacity it creates for future capability additions. The original mission computer architecture had run out of processing headroom before the full Block 4 capability could be implemented, meaning that some capabilities that the program had planned to deliver could not be added without first replacing the hardware. Technology Refresh 3 clears this constraint, providing sufficient processing margin not only for Block 4's full capability set, but for the planned Block 5 and subsequent upgrades that will continue the F-35's capability evolution over the coming decades. The specific capabilities that Block 4 and Program Increment 14 add to the F-35 include improved synthetic aperture radar imagery resolution from the APG-81, enhanced ground-moving target indication for better tracking of moving vehicles in complex terrain, advanced electronic attack modes that expand the threat systems the aircraft can suppress, improved identification friend or foe interrogation capability using the latest Mode 5 and Link 16 identification standards, and integration of new precision-guided munitions including the full Block 4 capability set will represent a substantially more capable aircraft than the aircraft that declared initial operational capability in 2015 and 2016, and that improved aircraft will be the standard configuration for the F-35 fleet through the late 2020s and into the 1930s. The production program at Lockheed Martin's Fort Worth facility has now delivered over 1,100 aircraft to customers across the program, representing over 1,100 of the eventual planned production of roughly 3,400 aircraft for all customers. The learning curve effects of this volume have driven the unit production price of the F-35 Alpha from its peak of over $100 million per aircraft in early production lots to the current range of approximately $77 to $80 million, with the expectation of further reductions as production volume increases and manufacturing efficiency continues to improve. This price trajectory is important for the program's long-term procurement plans because several allied nations have procurement commitments that are sensitive to unit costs and whose planned purchase quantities could be affected if costs rise. The allied customer base for the F-35 has continued to grow since the program's founding partner nations signed their participation agreements in the 1990s. Beyond the 8 founding partners, numerous additional nations have purchased or committed to purchasing F-35As through foreign military sales including Japan, South Korea, Singapore, Israel, Belgium, Poland, Finland, Switzerland, Canada, Greece, and the Czech Republic. This represents the most widely proliferated fifth-generation fighter program in history and creates an allied air power interoperability network of unprecedented scale. When allied nation F-35 fighters can share sensor data, targeting information, and tactical pictures over MED-EL with American F-35ers, the entire coalition operates as a more capable, more integrated force than the sum of individual national contributions would suggest. The F-35 program's relationship with the broader American defense industrial base extends well beyond Lockheed Martin's Fort Worth assembly facility. The prime contractor relationship encompasses a supply chain of hundreds of companies across the United States and allied partner nations. Pratt & Whitney, based in East Hartford, Connecticut, produces the F-135 engine. Northrop Grumman, the principal subcontractor, produces the center fuselage at its facility in Palmdale, California, and also develops the mission systems software together with Lockheed Martin. BAE Systems produces the aft fuselage and empennage. L3Harris produces the electronic warfare systems. Elbit Systems of America contributes the helmet-mounted display system. These companies and hundreds of others form a distributed manufacturing and integration network that is as much a national security asset as the aircraft itself. The strategic significance of this industrial base extends to the allied partner nations. Dutch company GKN Fokker produces composite structural components. Italian company Leonardo produces wing components at its facility in Chieri, Italy, where Italy's FACO, or Final Assembly and Checkout Facility, also performs final assembly of aircraft destined for Italian and other European customers. The Norwegian company Kongsberg produces aft fuselage components and has received workshare in recognition of Norway's partner nation status. This distributed production creates industrial stakes in the program's continuation in multiple allied democracies, providing a degree of political durability to the program's long-term procurement plans that a purely American production program would lack. The F-35's future is defined by its role in a threat environment that has continued to evolve since the program's requirements were written in the 1990s. China's development of the J-20 stealth fighter, which has been operational with the People's Liberation Army Air Force since 2017, and the ongoing development of additional fifth-generation and sixth-generation designs, creates an adversary air-to-air threat that the F-35's beyond visual range engagement capability must be able to defeat. China's continued investment in advanced integrated air defense systems, including the HQ-9 long-range surface-to-air missile and the more advanced systems currently in development, creates the same kind of defended airspace penetration challenge over the Taiwan Strait and the South China Sea that the F-35 was designed to handle over European and Middle Eastern threat environments. The program's response to these evolving threats is the Continuous Capability Upgrade Program that Technology Refresh 3 and Block 4 represent. The open mission systems architecture that was a design premise of the F-35 from its early days provides the mechanism for incorporating new electronic warfare techniques, new sensor processing algorithms, and new weapons as they are developed. The aircraft's physical airframe has useful life measured in decades and flight hours measured in the thousands, providing the platform onto which successive capability upgrades can be loaded as the threat environment demands. The Collaborative Combat Aircraft Program, which the Air Force is pursuing to develop semi-autonomous uncrewed aircraft that can team with the F-35 in combat, represents the most significant near-term addition to the F-35's operational concept. These aircraft, which will fly alongside F-35ers as loyal wingmen, can carry additional weapons, provide additional sensor coverage, take on higher-risk elements of a mission, or fly ahead of the F-35 formation to develop the threat picture before the crewed aircraft enter the engagement area. The F-35's data link architecture and mission systems computing capacity are designed to accommodate the command and control of these teaming aircraft, making the F-35 the control node for a mixed crewed and uncrewed formation in much the same way that the AH-64 Apache serves as the control node for the MQ-1C Gray Eagle in Army aviation. The sixth-generation fighter programs currently in development, including the next-generation air dominance platform in the United States, the British-Italian-Japanese Global Combat Air Program, and the French-German Future Combat Air System, will eventually provide a successor generation of crewed fighters with capabilities beyond what the F-35's airframe can achieve through upgrades alone. But these programs are still in development, and the first aircraft from them are not expected to enter service for at least another decade or more. For the foreseeable future, the F-35 is a capability. It is what American and Allied air forces will fight with against the most demanding adversary air defenses. And Operation Epic Fury has provided the most rigorous real-world validation of its effectiveness that any program manager could ask for. The F-35 that landed at a Middle Eastern airbase with a shrapnel wound in its pilot and battle damage on its airframe on March 19, 2026, had just done something no fighter aircraft in history had done before in confirmed combat. It had been hit by an enemy surface-to-air missile engagement in defended airspace, and it had flown home. The pilot survived. The aircraft was recovered. The program delivered on its promise. The F-35 Lightning II began as an attempt to replace aging fighter fleets across 3 services with a common platform that could penetrate the defended airspace of a sophisticated adversary, collect and distribute intelligence from inside that airspace, and deliver precision effects against target sets that no other aircraft could safely approach. It grew into the most expensive weapons program in human history, the most technically complex fighter aircraft ever built, and the cornerstone of American and Allied air power for the next generation of military aviation. In Operation Epic Fury, flying over Iran from the opening night of the campaign through its final days, the F-35 proved every claim its designers made about what it could do and where it could go. The aircraft that penetrated Iran's integrated air defense network from the first minutes of the campaign, that flew over the most defended target complexes in the country and came home, that when it finally took a hit did exactly what its engineers had designed it to do, that aircraft is not just a remarkable piece of engineering. It is the reason the campaign achieved what it achieved. The reason American forces were able to strike over 10,000 targets in 39 days, systematically dismantling the military infrastructure of a nation that had spent decades building defenses specifically designed to prevent exactly that outcome. The reason the pilot who flew into the most defended airspace in the Middle East and absorbed a surface-to-air missile engagement came home alive. The F-35 Lightning II is not merely an airplane, it is the architecture of American air dominance, and Operation Epic Fury is its definitive proof of concept. To fully understand the F-35's dominance in Operation Epic Fury, it is worth examining what the alternative would have looked like. Consider the challenge that confronted American air planners in the days before the campaign launched. Iran's integrated air defense network, as described earlier, was layered and redundant. But it was also adaptive. Iranian air defense commanders had studied American air campaigns going back to Desert Storm. They had watched the suppression of Iraqi air defenses in 1991, the NATO campaign against Yugoslavia in 1999, and the opening phases of Iraqi freedom in 2003. They had drawn lessons from each of those campaigns about how to survive American air attacks, how to complicate suppression of enemy air defense missions, and how to make the cost of operating in their airspace unacceptably high for conventional platforms. One of the central lessons Iranian planners drew from those campaigns was that fixed, continuously emitting radar systems are vulnerable. An air defense radar that transmits continuously on a fixed frequency can be located by anti-radiation missiles, jammed by electronic attack aircraft, and struck with precision-guided munitions guided by the radar's own emissions. Iran's response was to build an air defense network that included significant numbers of road mobile systems that could move between engagements, could be dispersed across the country rather than concentrated at predictable locations, and could operate in emission-silent modes where the radar is switched off except for brief intervals, reducing the window during which an anti-radiation missile can guide to the emitter. The Bavar 373 in particular was designed with mobility and emissions management as core requirements. Iranian crews trained extensively on deploying the system from road march, setting up in a new position, executing an engagement, and displacing before a retaliatory strike could arrive. The system's command and control architecture allowed individual batteries to receive targeting information from external sensors, including passive electro-optical systems, and cued by data from other batteries that had briefly illuminated a target, reducing the need for each battery to transmit its own radar emissions. Against this kind of distributed, mobile, emissions-disciplined air defense network, the conventional approach of flying growlers in suppression orbits while strike aircraft dash through the defended area becomes much less reliable. You cannot reliably suppress what you cannot reliably locate. The F-35's approach to this problem is fundamentally different from the Growler Plus conventional Striker model. Rather than operating outside the defended area while trying to suppress what is inside it, the F-35 operates inside the defended area, using its own sensors to locate threat systems from positions that no other aircraft can safely occupy. When an Iranian battery switches on its radar for a brief emission to engage an aircraft it thinks it has detected, the F-35, which may be flying directly over the battery's position at that moment, detects the emission at close range with high precision, geolocates the battery to within meters, and transmits that location to the strike planning cycle before the battery has completed its engagement sequence. The battery has revealed its location to try to engage a target it was never going to successfully track, and in doing so, it has signed its own targeting order. This inside-out intelligence collection model, where the penetrating aircraft is the primary sensor for locating the air defense systems that are trying to shoot it down, is what makes the F-35 qualitatively different from any previous approach to contested airspace operations. The aircraft is not just surviving the threat environment, it is exploiting the threat environment, using the adversary's attempts to engage it as an intelligence collection opportunity that systematically builds the targeting picture needed to destroy the air defense network. Each F-35 sortie into Iranian airspace was not just a strike delivery mission. It was an intelligence collection mission that made the next strike delivery mission easier and safer for every aircraft in the force. The electronic order of battle that the F-35 fleet accumulated over the first weeks of Operation Epic Fury provided a picture of Iran's remaining air defense capabilities that was updated in near real time and was more comprehensive than anything American intelligence had previously possessed. Traditional signals intelligence collection against Iran's air defense systems relied on surveillance platforms operating in international airspace or from satellite coverage, neither of which can match the collection quality available from a sensor flying directly through the defended area. The F-35 sensors, operating from inside the air defense network, collected emissions data and optical imagery from aspects and ranges that overhead and standoff collection simply cannot achieve. This targeting data fed directly into the Tomahawk strike planning that continued throughout the campaign. When an F-35 sortie identified the current position of a previously mobile Bavar 373 battery, that geolocation was fed into the strike queue, and a Tomahawk was retasked to that updated position within hours. The mobile air defense battery that Iranian planners had counted on being difficult to target because of its mobility, was being destroyed within hours of revealing its position because the F-35 was inside the defended area collecting the position data. The campaign's targeting cycle time, the interval between the detection of a target and the delivery of effects against it, compressed throughout the weeks of epic fury as the intelligence picture became richer and the strike planning process became more efficient at processing F-35 sensor data into actionable targeting products. By the campaign's second and third weeks, the combination of F-35 sensor collection, persistent overhead surveillance from unmanned aircraft operating in the outer threat rings, and the signals intelligence from RC-135 rivet joint aircraft provided a near-continuous awareness of Iranian air defense activity that allowed strike planners to respond to mobile threats with a speed that Iranian commanders had not anticipated and could not adapt to quickly enough. The F-35's role in air-to-air combat during the campaign deserves examination, even though Iran's Air Force made no effective challenge to American operations during Epic Fury. The reason Iran did not challenge the campaign from the air is itself a statement about the capability the F-35 and the F-22 together represented. Iranian Air Force commanders, looking at what American stealth fighters had done over their airspace in the opening days of the campaign, understood that any aircraft they launched to intercept the strike packages would be facing opponents they could not detect, could not engage beyond visual range with any reliable success, and would have no meaningful defensive options against once the F-35 or F-22 launched its beyond visual range missiles. Iranian F-14A Tomcats, the vintage American fighters that Iran has maintained in service since the pre-revolutionary period, when they were supplied to the Shah, are capable aircraft in the right circumstances. In a beyond visual range engagement against an F-35 that they cannot see and that is already inside their radar's detection range before they know it exists, they would be irrelevant. The Iranian calculation was rational. Sending aircraft to challenge the American campaign would have accelerated the destruction of the Iranian Air Force without meaningfully slowing the strikes. Iran focused its active resistance on ground-based systems, particularly the road-mobile batteries, and on proxy force operations through the drone and missile attacks that its allied groups continued to prosecute throughout the campaign. The F-35's air-to-air capability was decisive not by being used, but by being so obviously superior that the adversary chose not to contest it. This deterrence effect, the ability to shape adversary behavior through demonstrated or credibly threatened capability, is one of the most important contributions the F-35 makes to American military power. It does not have to shoot down Iranian fighters to prevent Iranian fighters from flying. Its existence and demonstrated performance in the first days of the campaign was sufficient to make Iranian air defense commanders conclude that committing their remaining air assets would be futile. This operational deterrence compressed the challenge American forces faced, allowing them to concentrate on the ground-based threat environment rather than managing simultaneous air-to-air and surface-to-air threats. The tanker support architecture that sustained the F-35's operational tempo throughout the campaign is itself worth examining as an element of the platform's operational picture. The F-35 has a large internal fuel capacity, particularly in the Charlie variant with its enlarged wing. But the distances involved in striking targets throughout Iran from carrier positions in the Arabian Sea and from land bases in the region meant that virtually every mission required at least one aerial refueling. The tanker fleet, operating primarily with KC-135 Stratotankers and KC-46 Pegasus aircraft from bases throughout the region and from Tel Aviv's Ben Gurion Airport, flew continuous refueling orbits over Iraq, Jordan, and the northern Persian Gulf, enabling the combat aircraft to take on fuel both inbound to Iranian targets and on the egress back to base. The scale of this tanker effort was enormous. Multiple reports documented tanker callsign patterns that indicated dozens of tanker sorties daily, with KC-135s flying 7-plus-hour sorties from Tel Aviv and other regional bases to maintain continuous refueling tracks. The willingness of regional partner nations to allow their territory and airspace to be used for this support infrastructure was itself a significant political and military achievement, reflecting the depth of the security relationships that American diplomacy had cultivated over decades. Without these regional basing and overflight permissions, the operational tempo of the campaign would have been severely constrained. The F-35's receiver compatibility with both the Air Force's flying boom refueling system and the Navy's probe and drogue system gives it flexibility to take fuel from any tanker in the American or Allied inventory. The aircraft's refueling receptacle is positioned on the upper fuselage behind the cockpit for the boom system and uses a retractable probe for drogue refueling. This dual compatibility means that carrier-based F-35 Charlies can refuel from the same KC-135 tankers that Air Force F-35As use, integrating the tanker architecture across service lines in a way that maximizes the efficiency of the refueling infrastructure. The precision of the weapons the F-35 delivered throughout the campaign deserves specific attention, because precision is what makes high-tempo strike operations against a dense and varied target set feasible, without the kind of civilian casualties that would have generated unsustainable political pressure on the campaign. The JDAM-guided weapons that constituted the primary strike payload are accurate to within approximately 5 meters of their designated coordinates regardless of weather, which matters enormously in a campaign that continues night after night through whatever meteorological conditions prevail. The Stormbreaker's moving target capability addressed the specific challenge of mobile systems, including the Road Mobile Air Defense Batteries and the fast attack watercraft operating in the Strait of Hormuz, that previous precision-guided weapons with GPS-only guidance could not reliably engage. The campaign's targeting process, which determined what coordinates were entered into each weapon's guidance system, itself benefited from the F-35 sensor collection. The synthetic aperture radar imagery that F-35ers generated of Iranian facilities as they flew over them provided targeting coordinators with the most current possible picture of each facility's layout, identifying the specific structures where high-value activities were occurring and allowing them to direct weapons to the precise aim points that would achieve the desired effect. This combination of a penetrating sensor platform that could collect from directly overhead and a precision-guided weapons suite that could destroy precisely what the sensor identified compressed the time from intelligence collection to effects delivery in ways that previous generations of air campaign architecture could not achieve. The F-35's performance throughout Operation Epic Fury also validated specific design choices that had been controversial during the program's development. The decision to use a single engine rather than the twin-engine configuration of the F-22 and F-15E was debated extensively during the program's early years, with critics arguing that single-engine reliability over water and over hostile territory was unacceptable for a carrier aircraft and a combat aircraft expected to fly deep into defended airspace. The Pratt & Whitney F-135 engines demonstrated reliability throughout the campaign with no confirmed engine-related losses across thousands of combat sorties, validated the single-engine design choice. The engine's performance in the high-altitude, high-temperature environments encountered during operations throughout the region demonstrated the robustness of the design in real operational conditions rather than the controlled conditions of a test range. The decision to accept somewhat lower maximum speed than fourth-generation fighters was similarly vindicated by the campaign. The F-35's Mach 1.6 top speed was adequate for every mission profile flown during Epic Fury, and the aircraft's ability to complete those missions without being detected or engaged in the vast majority of sorties demonstrated that speed is not the primary determinant of survivability in the threat environment the aircraft was designed for. Being invisible at Mach 1.2 is more survivable than being detectable at Mach 2.4. The question of how the F-35 compares to the F-22, the other American fifth-generation fighter, is one that the campaign illuminated in useful ways. The F-22's role in Epic Fury was primarily air superiority, providing the combat air patrol coverage that protected the strike packages from any Iranian airborne challenge. The F-22's superior speed, altitude ceiling, and agility at high angles of attack make it the more capable pure air superiority fighter for within visual range and closing beyond visual range engagements. But the F-22 lacks the multi-role sensor suite, the ground attack capabilities, and the data link architecture that make the F-35 the Joint Forces' primary sensor collector and strike deliverer inside defended airspace. The two aircraft are genuinely complementary rather than redundant. The F-22 creates the conditions under which the F-35 can operate by dominating the airborne threat environment. The F-35 exploits those conditions by penetrating the surface-based threat environment and delivering effects against the full range of targets the campaign requires. The lessons that Operation Epic Fury has generated for future F-35 employment doctrine will take years to fully analyze and incorporate into the training and tactics that shape how crews prepare for the next major air campaign. But some themes are already apparent. The F-35's ability to serve as the Joint Forces Forward Sensor Node, collecting targeting data from inside the defended area and transmitting it to the strike planning cycle in near real time, will drive investment in the data link architecture and the processing systems that allow that data to be rapidly converted into actionable targeting products. The demonstrated vulnerability of even road mobile air defense systems to F-35-enabled targeting cycles will shape how adversaries attempt to adapt their air defense employment concepts, driving further investment in emissions management, deception, and passive engagement techniques that the F-35 community will need to develop counters to. The campaign also highlighted specific areas where additional capability investment would enhance the F-35's effectiveness. The aircraft's current weapons suite, while comprehensive, does not include a hypersonic strike weapon, and the development of longer-range hypersonic weapons that could be carried internally in the F-35's bays would extend the aircraft's ability to strike deeply defended targets without requiring overflight of the target area. The integration of advanced artificial intelligence processing in the mission computer's sensor fusion and threat assessment functions would allow the aircraft to process even richer sensor environments with greater confidence in target identification, reducing the probability of misidentification errors in cluttered environments. And the continued development of the collaborative combat aircraft teaming concept, with semi-autonomous wingman aircraft extending the F-35 sensor and weapons reach, represents the most significant near-term enhancement to the platform's combat power. The ground crews and maintenance personnel who supported the F-35 operation throughout Epic Fury deserve recognition as a critical element of the system's performance. An aircraft can only fly as many sorties as its maintenance crews can prepare it for, and the logistics chain that kept 30-plus F-35 Alphas flying combat missions day after day from Lakenheath and regional bases, while simultaneously supporting carrier operations on the Abraham Lincoln and managing the supply of spare parts, specialized maintenance tools, and the software updates that continue throughout the campaign, represented a maintenance and logistics achievement of the first order. The Autonomic Logistics Information System's predictive maintenance capability contributed to keeping aircraft available at the rates the campaign's tempo demanded, but it was the aircrew chiefs, avionics technicians, engine mechanics, and low observable specialists who made the predictions actionable and kept the aircraft in the fight. The F-35's low observable surface maintenance requirements were one of the more demanding aspects of sustaining the fleet through a high-tempo combat deployment. The radar-absorbing coatings applied to the aircraft's surfaces degrade through the normal wear of flight operations, through the heat of engine exhaust, through the mechanical stress of weapons bay door cycling, and through the atmospheric effects of high-altitude flight in the Middle Eastern environment. Maintaining these surfaces to the specifications required for the aircraft's stealth performance to meet its design intent requires regular inspection using specialized equipment and repair using materials that are themselves carefully controlled and precisely applied. In an operational environment where aircraft are turning around for the next mission within hours of returning from the last one, the time available for low observable maintenance is constrained, and the prioritization decisions made by maintenance officers about which aircraft needed immediate attention and which could continue flying with acceptable surface condition degradation were operational decisions as much as maintenance decisions. The long-term strategic significance of the F-35's performance in Operation Epic Fury extends far beyond the campaign itself. The demonstration that a stealth fighter can penetrate the air defenses of a sophisticated adversary nation, collect intelligence from inside those defenses, deliver precision effects against the highest priority targets, and sustain this capability across thousands of sorties in a 39-day campaign, has implications for every potential adversary that might consider challenging American interests. China's military planners, who have invested heavily in air defense systems specifically designed to hold American aircraft at risk in the Western Pacific, now have a data point that was not available before February 28, 2026. Their systems did not succeed in reliably detecting and engaging the F-35. The modifications they will make to their concepts of operations in response to that data point, and the countermeasures they will invest in, will shape the next generation of the stealth versus air defense competition that has been the central technological and operational tension in air warfare for 3 decades. The F-35 program's contribution to this competition is not static. The continuous upgrade architecture, the investment in advanced electronic warfare capabilities, and the development of teaming concepts with collaborative combat aircraft all represent American investment in staying ahead of the evolving adversary countermeasures. The Air Force's next-generation air dominance program, whatever form its eventual product takes, will itself be designed with lessons from the F-35's operational experience, including the lessons of Operation Epic Fury, baked into its requirements. American air power does not rest on the F-35 alone, but for the foreseeable future, the F-35 is where the most important decisions in the competition between stealth and air defense get made and tested, and the evidence of the past few months suggests that those decisions have been, on balance, the right ones. The 39th night of Operation Epic Fury looked different from the first. Iranian air defense activity had been substantially reduced across most of the country. The facilities that had defined Iran's nuclear program, its ballistic missile capability, and its ability to project power through proxy forces had been destroyed or severely damaged. The Strait of Hormuz, which Iranian commanders had threatened to close through mine-laying and fast-attack boat operations, was open to shipping under American naval escort. The proxies in Iraq, Syria, and Yemen who had been attacking American and Allied targets throughout the campaign had been degraded in their capability and had reduced their operational tempo in response to the sustained pressure. None of this had been achieved cheaply or without cost. 13 American service members were killed during the campaign. Hundreds were wounded. Dozens of aircraft were lost or damaged. The American taxpayer had funded an air campaign of enormous scale and had committed some of the most expensive military hardware ever produced to sustained combat operations. And through all of it, the aircraft that had been present from the first second to the last, that had penetrated where nothing else could penetrate and done what nothing else could do, was the F-35 Lightning II. The pilot who flew the damaged F-35 home on March 19th did not do so because of luck, or because the aircraft survived through an accident of fate. The aircraft absorbed a hit that would have killed a fourth-generation fighter, because 50 years of investment in stealth aerodynamics gave it a radar cross-section that forced Iranian radar systems to engage at shorter ranges with less tracking time than they needed for a high-probability kill. Because the F-135 engine's design included fault-tolerant features that allowed it to continue operating after the kind of damage that killed less robust power plants. Because the flight control system's redundant hydraulic and electrical architectures ensured that control authority was maintained even with damaged actuators and severed signal paths. Because the cockpit's blast-resistant transparency and the pilot's pressurized flight suit limited the effects of the shrapnel that entered the cockpit. Every one of those design choices had been made decades earlier by engineers at Lockheed Martin, Pratt & Whitney, and dozens of supplier companies who were designing for exactly this scenario. The pilot survived because the program delivered. The F-35 Lightning II is the product of 30 years of development, hundreds of billions of dollars of investment, the contributions of 8 founding partner nations and dozens of subsequent customers, and the accumulated operational experience of every combat deployment from Syria in 2018 to Iran in 2026. It is the most capable, the most sophisticated, and by every objective measure the most effective multi-role fighter aircraft in the history of aviation. Its critics are correct that it cost more than was initially promised, and took longer to develop than the program originally projected. They are also correct that it represents specific performance trade-offs that were made in service of capabilities those critics undervalue. What the critics could not foresee, because the evidence was not yet available when most of the critical accounts were written, is what the aircraft would do when it was actually put to the test. Now the evidence exists. Over Iranian airspace, in the most demanding air defense environment that American aviation has ever operated in at this sustained tempo, the F-35 performed exactly as its designers said it would. It penetrated, it struck, it survived, it came home, and it did it over 10,000 times before the campaign was over. That is the F-35 Lightning II. That is its legacy. And it is only getting started. The pilot training pipeline that produces F-35 aircrew is itself a reflection of the aircraft's complexity and the demands it places on the human beings who fly it. Unlike previous generations of fighter training, where the fundamental challenge was teaching a pilot to fly the aircraft to its physical performance limits, and then training the employment of weapons in relatively straightforward tactical scenarios, F-35 training centers on a different kind of cognitive challenge. The aircraft can outperform any human's ability to manage all of its systems simultaneously in their raw, unintegrated form. The sensor fusion architecture exists precisely because no human pilot could monitor 6 separate sensor displays, process the electronic warfare suite's emissions data, manage the data link traffic from multiple aircraft, track 20 simultaneous contacts on the radar, and fly an aggressive low-altitude attack profile at the same time. What F-35 training teaches is how to work effectively with the aircraft's integrated systems, understanding what the fused picture is telling you and when to trust it versus when to interrogate it, knowing how to manage the sensor suite's modes and priorities to optimize the picture for the tactical situation you are in, and developing the judgment to make kill-chain decisions under time pressure when the aircraft systems have provided a high-confidence target identification. This is a different cognitive skill set than previous fighter training emphasized, and the training pipeline at Luke Air Force Base in Arizona, where the F-35 formal training unit is located, has had to develop new instructional methodologies and new simulation facilities to teach it effectively. The simulators used in F-35 training are themselves among the most sophisticated military training systems ever built. The Weapon Systems Trainer, known as the WST, replicates the full cockpit environment with all of the aircraft systems functioning as they would in the actual aircraft, including the sensor suite, the data link architecture, the weapons management system, and the helmet-mounted display. The simulator can inject any tactical scenario, populate the simulated airspace with as many threats and friendly forces as the scenario requires, and exercise the pilot against the kinds of complex, multi-threat environments that actual combat in a sophisticated air defense environment involves. The fidelity of the simulation is high enough that pilots transitioning from the simulator to the actual aircraft report that the experience is familiar in the ways that matter for tactical decision-making, even if the physical sensations of flight cannot be replicated. The training syllabus progresses through a series of building block phases that develop the pilot's ability to integrate the aircraft systems in progressively more complex tactical scenarios. Early phases focus on basic aircraft handling, system familiarization, and single aircraft employment against simple threat environments. Later phases introduce multi-ship tactics, complex electronic warfare environments, and the integration of the F-35's data link architecture with the broader joint force. Final phases exercise the full range of mission types that operational crews will encounter, from night low-level strike missions against heavily defended targets to combat air patrol in a contested airspace environment with multiple airborne and ground-based threats. The training syllabus also addresses the unique challenges of operating an aircraft whose stealth performance is a maintained characteristic rather than a fixed physical property. Pilots are trained to understand how their aircraft's low observable characteristics are affected by the weapon's configuration, the altitude and airspeed, and the condition of the low observable coatings, and to make employment decisions that account for these variations. A pilot who understands that carrying an external weapons load in beast mode increases the aircraft's radar cross-section significantly will plan ingress and egress routes differently than when flying with a clean internal-only loadout. This kind of nuanced understanding of how stealth performance varies with configuration and mission profile is part of the tacit operational knowledge that F-35 training seeks to develop. The squadron culture around the F-35 at operational units like the 48th Fighter Wing at Lakenheath has also evolved to reflect the aircraft's unique characteristics and employment concepts. Mission planning for F-35 operations is more data-intensive and more analytically demanding than for fourth-generation aircraft. Because the full exploitation of the aircraft's sensor fusion and networking capabilities requires careful coordination of sensor coverage, data link assignments, and the routing of information through the joint force architecture. Mission debrief processes have been redesigned to capture the electronic warfare and sensor data that the aircraft records during each flight, providing an objective picture of what the aircraft systems saw and what decisions were made, which allows more systematic identification of training points and tactical lessons than the traditional pilot memory-based debrief process. The maintenance culture around the F-35 is similarly demanding. The aircraft's low observable surface maintenance requirements mean that maintainers must be trained not just in the mechanical and electronic systems of the aircraft, but in the specialized materials and techniques required to inspect and restore the radar-absorbing coatings. This is skilled work that requires certification and regular recertification, and it represents a significant addition to the maintenance personnel requirement compared to fourth-generation aircraft. The logistics chain that supplies the materials needed for this maintenance must be carefully managed, because the specific materials used for different areas of the aircraft surface are not interchangeable and must be matched to the design specifications for each location. The weapons loadout and configuration management for F-35 operations is also more complex than for conventional fighters, because the internal weapons bay configuration affects the aircraft's aerodynamics, weight distribution, and load balancing in ways that the weapons management system must account for. Ordnance personnel loading weapons into the internal bays work in tighter physical constraints than those loading conventional external pylons, and the sequence and positioning of stores in the bays must be carefully managed to maintain the aircraft's center of gravity within its flight envelope limits. The broader operational support infrastructure that surrounds the F-35 fleet includes dedicated intelligence analysis cells that process the sensor data the aircraft collects and convert it into targeting products, mission planning systems that integrate the aircraft's specific routing and configuration requirements with the Joint Forces Strike Planning process, and communications infrastructure that manages the data link traffic between F-35ers and the various elements of the joint force they communicate with. This support infrastructure is as much a part of the F-35 system as the aircraft itself, and building and sustaining it at the units that operate the aircraft is an ongoing investment that is often less visible than the aircraft procurement numbers, but is equally important to the capability the aircraft delivers. The F-35's contribution to American national security extends beyond the specific military missions it performs. The program has generated significant advances in manufacturing technology, materials science, software engineering, and system integration that have spillover benefits for both the defense industrial base and the broader commercial aerospace sector. The composite material manufacturing techniques developed for the F-35 airframe have applications in commercial aircraft structures. The software validation methodologies developed for the mission systems have influenced practices in other safety-critical software domains. The systems engineering approaches used to manage the integration of hundreds of subsystems from dozens of suppliers have informed program management practices across the defense industrial base. The economic footprint of the F-35 program is substantial. The program supports approximately 200,000 jobs across the American economy in manufacturing, engineering, logistics, and support roles at companies distributed across most of the 50 states. The program's reported annual economic contribution to the United States economy has been cited at approximately $79 billion, reflecting both the direct employment and the broader supply chain and induced economic activity that the program generates. These economic benefits are relevant to the program's political sustainability because the distribution of economic activity across many congressional districts creates a broad constituency for continued program support that has helped sustain procurement funding through the difficult years of cost overruns and schedule delays. The question of the F-35's cost-effectiveness relative to the alternatives deserves a final direct treatment. The aircraft is expensive. A single F-35 Alpha in current production costs approximately $77 to $80 million. The total program cost, across all variants and all planned procurement, is hundreds of billions of dollars. The lifecycle cost, encompassing operations, maintenance, upgrades, and support across the expected service life of the fleet, is projected to be measured in trillions. These are genuinely large numbers by any standard. But the relevant comparison is not between the F-35's cost and zero cost. It is between the F-35's cost and the cost of the alternatives, which include not just the procurement cost of different aircraft, but the operational cost of the losses that would be sustained if less capable platforms were used in the missions the F-35 performs. In Operation Epic Fury, 5 crewed fighters were shot down and the crews of 4 of them were lost or put in extreme peril. All 5 were 4th-generation aircraft. The one 5th-generation aircraft that was hit flew home with its pilot alive and the aircraft recoverable. If the 30 F-35 Alphas that flew combat missions in Epic Fury had been 30 F-16Cs instead, and if those F-16Cs had attempted to fly the same missions into the same defended airspace, the attrition rate would have been fundamentally different. Not because F-16C pilots are less skilled or less brave, but because the physics of radar cross-section, sensor integration, and electronic warfare capability that protect the F-35 do not protect the F-16C. The cost of the F-35 is the cost of keeping American aircrew alive while accomplishing missions that need to be accomplished in the most demanding operational environments. When evaluated against that standard, the investment is not a question of affordability. It is a question of what value American society places on the lives of the men and women who fly into harm's way to execute the nation's defense strategy. The program's answer, built into every system, every design choice, every dollar of development investment, is that the answer is very high. The F-35 exists to give American aircrew the best possible chance of coming home from the missions that need to be flown. And on March 19, 2026, over Iran, it delivered on that commitment in the most direct and measurable way possible. The F-35 Lightning II's story is not finished. The aircraft currently in service will fly for decades. The capabilities it carries will continue to be upgraded through successive software and hardware improvement programs. The allied nations that have bought it will continue to integrate it into their national defense architectures. The adversaries that have encountered it will continue to develop countermeasures, driving further American investment in electronic warfare, new weapons, and the uncrewed systems that will fly alongside it in future campaigns. The sixth-generation fighters that will eventually succeed it in the most demanding missions are still years away from operational service, and, in the meantime, the F-35 carries the weight of American air power's future on its stealth-coated airframe. The 30-year journey from the DARPA ASTOVL program to the skies over Iran has produced an aircraft that is, by the evidence of its operational record, exactly what its designers said it would be. It is survivable where other aircraft are not. It is effective where other aircraft cannot operate. It sees what other aircraft cannot see and knows what other aircraft cannot know. And when it is hit, it flies home. The F-35 Lightning II is the tip of the spear. Operation Epic Fury proved it. And the next campaign, wherever it comes, will prove it again. The geopolitical consequences of the F-35's performance in Operation Epic Fury are still unfolding, but several threads are already clear enough to examine. The first and most immediate is what the campaign communicated to China. Beijing's military planners have spent the better part of 2 decades building what they call anti-access and area denial systems, a layered architecture of long-range surface-to-air missiles, over-the-horizon radars, anti-ship ballistic missiles, and electronic warfare capabilities designed to make it prohibitively costly for American forces to operate in the Western Pacific in a conflict over Taiwan or the South China Sea. The intellectual foundation of this strategy was the belief that American air power, effective as it had been against the primitive defenses of Iraq and Afghanistan, would be unable to sustain operations against a sophisticated, integrated, multi-layered defense network of the kind China was building. Operation Epic Fury did not involve Chinese anti-access and area denial systems. Iran's integrated air defense network, while capable, is not equivalent to what China can deploy in the Western Pacific. But the campaign demonstrated something that is transferable across that difference. It demonstrated that the American approach to penetrating a sophisticated layered air defense architecture, an approach centered on the F-35 as the forward sensor node and precision strike platform inside the defended area, working in combination with electronic warfare support from outside the defended area and long-range standoff weapons from even further out, is operationally effective in a way that Iran's best attempts at defense could not prevent. The specific performance metrics of the campaign, the sortie rates, the attrition rates, the target destruction rates, will be analyzed intensely by People's Liberation Army planners looking for indicators of how their own systems would perform in a comparable engagement. What they will find is that the core challenge they face in defending against the F-35 has not changed because of Epic Fury. The F-35's radar cross-section is what it is. The physics of millimeter wave radar cross-section are not subject to revision based on operational experience. The challenge for adversary planners remains exactly what it was before the campaign. How do you detect, track, and engage an aircraft that your radar sees as a golf ball when every other parameter of the tactical situation tells you a fighter is there? They have not solved this problem, and the investment required to solve it is enormous, uncertain in its eventual efficacy, and must be sustained over decades against an opponent who is simultaneously improving the aircraft's electronic warfare and stealth performance through each successive upgrade cycle. The second geopolitical thread is what the campaign communicated to American allies who had been considering or had already committed to F-35 purchases. Every nation that has bought or is considering buying the F-35 received a demonstration during Operation Epic Fury of the aircraft's combat effectiveness against a sophisticated air defense environment that no test range exercise could have provided. The governments and military establishments of those nations now have evidence, not just simulation results or theoretical analyses, that the aircraft they are purchasing performs as advertised in the most demanding operational environment it has yet faced. The political sustainability of F-35 procurement programs in countries where the cost has generated domestic political criticism is enhanced when the aircraft's combat performance in a real campaign becomes part of the national conversation about the program. Israel's relationship with the F-35 is particularly worth examining in this context. The Israeli Air Force's F-35A fleet participated in Operation Epic Fury both directly through Israeli strike operations that were part of the coalition effort and indirectly through the years of operational experience that Israeli crews had accumulated in the platform before the campaign began. Israel has been the most combat-experienced F-35 operator outside the United States, and the tactics, techniques, and procedures that Israeli crews developed through their operations in Syria and against Iranian proxy infrastructure inform the broader coalition understanding of how to employ the aircraft against the specific threat environment they would face. The Israeli F-35As modifications, including the integration of Israeli-developed electronic warfare systems and the ability to carry Israeli-developed weapons, represent a model of Allied customization that other F-35 operators are watching closely. The ability to integrate national-specific systems while retaining the core stealth architecture and sensor fusion capability of the standard platform gives Allied operators a degree of operational independence and a pathway for incorporating indigenous technology that enhances both national security and the political support for the program in countries with active defense industries. The third geopolitical thread is what the campaign communicated to potential adversaries other than China who might consider testing American military power in the coming years. North Korea, which has invested heavily in ballistic missiles and a modest air defense network, watched the destruction of Iranian nuclear and missile infrastructure with obvious interest. Russia, whose air defense systems including the S-400 are widely exported to nations that might someday face American air power, has had the performance of those systems against F-35 operations under contested conditions as a data point since Israel began operating in Syria in 2018 and now has a richer dataset from Iran's experience. The message that these observers receive from the F-35's performance is the same message that American deterrent strategy intends for them to receive. The cost of challenging American interests through military force is very high, and the assets that would be destroyed in the first hours of any such challenge are the ones that the challenging nation counts on most for its security. This deterrence effect, operating through demonstrated combat capability, is the most important contribution that the F-35 makes to American national security and to the security of the allies who have adopted the platform. It is not measured in sorties flown or targets destroyed. It is measured in the decisions that potential adversaries do not make, the challenges they do not attempt, the provocations they calculate would cost more than they are worth. The dollar cost of the F-35 program, enormous as it is, must be evaluated against this deterrence benefit, as well as against the kinetic military outcomes it produces in campaigns that actually occur. An aircraft that prevents wars through its demonstrated capability is worth more than one that is inexpensive, but fails to deter. The 39 days of Operation Epic Fury added substantially to the F-35's deterrence value. The aircraft had already demonstrated through Israeli operations in Syria and through American and British operations in lower threat environments that it could operate effectively in defended airspace and deliver precision effects against hardened targets. What Epic Fury added was the demonstration that this capability scales, that it can be sustained across thousands of sorties at high operational tempo, that it can penetrate the defenses of a nation that specifically invested in American access denial capabilities, and that even when the aircraft takes a hit, in the most demanding operational environment it has faced, it brings the pilot home. That combination of scale, sustainability, penetration, and crew survivability is the complete statement of what the F-35 program promised when it was conceived in the 1990s, and what it has been delivering since Israeli crews first flew it over Syria in 2018. The promise has been kept. The capability is real, and it will remain the cornerstone of American air power, and of the broader coalition of Allied air forces that have adopted it, for the next generation of whatever conflicts the world's future holds. The aircraft that was selected over the Yahweh 64 in 1976. Wait, that was the Apache. Let us stay with the F-35. The aircraft that won the Joint Strike Fighter competition over the Boeing X-32 in 2001 was not yet fully formed. It was a prototype demonstrator that had proven three specific capabilities in a flight test environment. What it has become over the 25 years since that selection, through the most demanding and most contested development program in the history of military aviation, is something that the engineers at Lockheed Martin's Advanced Development Programs Division, the facility known as the Skunk Works, could probably have told you it would become if anyone had been willing to listen. It would become the most capable multi-role fighter aircraft ever built. It would become the aircraft that nations with sophisticated defense industries and significant security threats chose to buy for their most demanding missions. And it would become the aircraft that, when the most important air campaign in a generation was launched, was at the tip of the spear from the very first second to the very last. The F-35 Lightning II, the tip of the spear, proven over Iran. The full measure of the F-35's achievement in Operation Epic Fury will take years to be properly documented and assessed by military historians and defense analysts. The operational security requirements that govern the release of specific sortie data, weapons employment figures, and the precise performance metrics of classified systems mean that much of the most important evidence of the aircraft's performance will remain classified for years or decades. What is already in the public record, the confirmed combat hit that the aircraft survived and flew home from, the 13,000-plus sorties the American force flew with only a single confirmed F-35 damage event, the systematic destruction of an integrated air defense network that had been designed specifically to threaten American aircraft, and the 39 days of sustained operations at a tempo that no previous air campaign against a comparable opponent had achieved. That record speaks clearly enough to anyone willing to read it without the filter of preconceived skepticism about what the program was capable of. The men and women who designed the F-35 over 30 years, who wrote the mission systems code, who machined the composite airframe components, who developed the radar-absorbing materials, who engineered the lift fan propulsion system for the Bravo variant, who integrated the helmet-mounted display with the DAS imagery, who validated the sensor fusion algorithms through millions of test cases on the Ironbird, all of them contributed to the outcome on March 19th when a damaged F-35 flew home with a wounded pilot aboard. They did not know, on the day they made each of the thousands of individual engineering decisions that collectively produced that outcome, that their work would be tested in exactly this way. They made those decisions based on requirements, documents, and physics and engineering judgment, and the decisions were right. That is the final word on the F-35 Lightning II. Not the cost numbers, not the schedule delays, not the congressional hearings, not the reformer community's critiques of its turn performance. The final word is March 19, 2026, over Iran, when the most advanced fighter aircraft in the world took a hit, flew home, and proved that 3 decades of engineering investment in doing exactly that was worth every dollar and every hour. The operational readiness rates that the F-35 fleet maintained throughout Operation Epic Fury, while the specific figures remain classified, were described by senior Air Force officials in general terms as sufficient to sustain the campaign's required tempo without significant operational pauses driven by aircraft availability. This is a noteworthy achievement for a platform whose early operational years were marked by availability challenges as the maintenance infrastructure matured, and as the predictive maintenance systems accumulated the data needed to make accurate prognostic assessments. The improvement in operational availability since the aircraft's initial operational capability declarations reflects both the maturation of the maintenance processes and the benefits of the Autonomic Logistics Information System's predictive maintenance architecture, which by the time of Epic Fury had accumulated years of fleet-wide operational data on component failure rates and maintenance requirements across the full range of operational environments in which the aircraft had been deployed. The F-35's operational availability in the heat and dust of the Middle East environment, which places demanding requirements on air filtration systems, cooling systems, and the electronic components that must operate reliably in ambient temperatures that exceed the design baselines for commercial electronic equipment, validated the environmental qualification work done during the development program. The aircraft was designed to operate globally, in environments ranging from Arctic Norway to equatorial Singapore, and the qualification testing that demonstrated operation across that environmental range was reflected in the aircraft's actual performance throughout a campaign that placed it in one of the more demanding thermal environments it would regularly encounter in operational service. The fact that the aircraft systems continued to perform reliably under these conditions, while sustaining the sortie rates required by a major air campaign, is evidence of the engineering margin built into those systems and of the maintenance culture that the program has developed at its operational units.